basics of and motivation for encrypted search. As this is an encrypted seminar, most of you might already know a lot about what I'm going to talk about, but it's always good to refresh. So let's start. In today's world, there is a huge amount of data that is stored and processed in databases on the cloud. This data includes our sensitive medical records, our secret and not so secret communications, our online shopping activity, financial information, etc. Um, Unfortunately for us, even if we trust the server that is storing the data, hosting the data, which should already be a big no. These databases are very unprotected from external adversaries that can break into the system and essentially steal the data. In recent past, as some of you might be aware, there have been a constant occurrences of data breaches. This is happening to everyone. Corporations, government agencies, small businesses, large businesses, the list goes on. The famous Equifax breach alone affected 148 million Americans. The eBay breach affected 145 million Americans, and this is collectively the population of the United States. Moreover, the Marriott breach is essentially a horror story. The attackers breached a system of a small chain of hotels called Starwood Hotels in 2014. Marriott acquired Starwood in 2016, only to discover in 2018 that the attackers had remained in the system for over 5 years. Over this time, they collected approximately 500 million customers across data on 500 million customers across the world, which included passport numbers, travel information, addresses, contact numbers, and like travel plans, itineraries, so much more. um, yeah, so this tells us that we need to keep this data safe from these attackers, and the need to do that is now more urgent than ever. So let's talk about how this data gets stolen. There are roughly two ways in which the databases, in which the data that is stored in these databases on the cloud can be stolen. Option one is the adversary compromises the application and just queries the data. And option two is the adversary compromises the the server database server itself, the server hosting the database itself. And we are more concerned with option number two here. So how do we keep this data safe from so many adversaries out there? One naive way is for a client to upload all its data to the server and then encrypt it. This will keep the data safe, but unfortunately, it will break services that these servers provide, such as search functionality or update functionality. It is undesirable that as a user, we download everything first, decrypt to run searches over the data locally. So we want to do essentially is to encrypt the data on the server and still be able to query or update it. So the question really is that can we encrypt databases even in use? And for quite some time, the answer has been yes, we can. There have been tons of research on this problem for the last 15 to 20 years. There have been solutions based on different cryptographic building blocks. For example, fully homomorphic encryption is one such building block. But solutions that involve fully homomorphic encryption are too slow and are space inefficient. Their search complexity grows linearly with the size of the database, which is far from optimal. But thankfully, there are sublinear solutions as well, where complexity doesn't grow like that. But before we get into those, um, we have um, we have to talk about this trade-off, which is between efficiency, functionality, and leakage. Efficiency is basically the practicality of your searchable encryption solution, how fast it works. Efficient functionality is basically how expressive or complex your queries can be in this solution. And leakage is essentially what the server learns from your query, update, or your data while observing the execution of the protocols in your solution. This trade-off essentially implies that if a client wants less leakage, they want to compromise. They have to compromise on efficiency and or functionality. If they want more efficiency, they have to leak more to the server and so on. So if leakage happens, we deal with it in literature. So researchers either do cryptanalysis where they try to exploit the leakage of various schemes and try to break those privacy guarantees that those schemes have, and to try to make a case against that scheme. Our researchers try to design low leakage solutions. which basically means the design schemes that have minimal leakage as possible, such that it is not prone to the attacks that you know the cryptanalysis guys write up. So in our work, I have tended to focus more on designing low leakage solutions, and this paper is in the same vein. So getting back to sublinear solutions for encrypted search, as opposed to fully homomorphic encryption, they do not have an overhead equivalent to database size. For example, we have ORAM-based solutions, oblivious RAM-based solutions, which exist, but they have a logarithmic overhead and they require multiple round trips between a client and a server. We have property preserving encryption, which opens doors to queries like range queries. That is to say, let's say I want the server to return everything that's greater than one particular value and less than another particular value. But these schemes have been prone to various attacks, much more so than other primitives that are in the same class. And finally, we have symmetric searchable encryption, SSE, or structured encryption, STE. STE is basically a generalization of SSE, and it tends to be most efficient and seems to have the best balance between leakage and efficiency. And in this work, we focus on STE low leakage solutions. And I'll go over what STE means exactly in the next slide. So now we quickly refresh what structured encryption or STE is. This is important for the rest of the talk because the whole talk revolves around STE. STE is one of the building blocks to achieve encrypted databases, and it is the way for us to basically privately query data structures, right? So let's say a client has a data structure with sensitive data in it. We call it DS. It's on the screen. Using the setup algorithm of the structured encryption scheme, which takes in a security parameter and the data structure, and it outputs a secret key, a secret cryptographic key K, and an encrypted data structure. Now, this encrypted data structure will then be sent to the server to be stored. The server we do not trust, as represented by the devil on the screen. And then the server might be able to learn something during the execution of this protocol. And from the encrypted data structure, such as the size of the input data structure, etc. This is basically what we call the setup leakage, and is like denoted by the setup leakage function ls, which is on the screen right now. So now what we essentially want to be able to do with this scheme is to be able to query or update our encrypted structure. So for query, a client can use a token algorithm, which takes in the key K and a query Q and outputs a token TK. The purpose of this token is essentially to hide the plain text query from the server. The server then, we send the token, this encrypted version of some query to the server. The server then runs the query algorithm, which takes in the encrypted data structure and the token and outputs an answer to the client. During the execution of this protocol, there could be leakage as server observes, such as the size of the result set, whether a search was repeated on the same token, and so on. And this is captured by the query leakage, or LQ, which takes in a data structure and a query queue. And in the same way, we have an update token algorithm, which is denoted by U token. U token algorithm takes in an update U and a secret key K and outputs an update token, UTK. The server uses this UTK to basically update the encrypted structure using an update algorithm. And the leakage during this protocol execution that the server observes is captured or denoted by LU, or the update leakage function. Okay, so now structured encryption is a way for us to query data structures privately. And the major data structure, which we'll keep going back to in this talk, is a multimap. So let's quickly refresh that in our minds. So multimaps map labels to tuples. as you can see in this multi-map on the screen, L1 is mapped to a tuple of size 3, which has 3 values, v1, v3, v4. And if multi-map have like get operations, and if we apply the get operation on L3, it basically returns us a tuple of size 2, v2 and v4. So fairly simple. But why do we care about these multi-maps? We care about these multi-maps because they're basically equivalent to an inverted index. An inverted index is a very powerful search primitive. Imagine we have a lot of records or documents, and these records or documents have identifiers. So the on the screen, if you see the inverted index has values that are like ID3, ID4, ID2. These are basically document identifiers. And these documents have various keywords, W1, W2, W3. An inverted index essentially stores the keywords as labels and the document identifiers as values. And then if you want to look up for, let's say, a keyword brown, you will simply get brown from the inverted index, and it will return to you a tuple of identifiers that identify the documents that contain the keyword brown. So from this point onwards, we'll instantiate our data structure with multi-map and our encrypted data structure with an encrypted multi-map, as you can see in the red on the screen. And also, if you look closely at the token that was sent to the server on the second big blue arrow, the tokens are basically some sort of encrypted version of the keywords that are contained in a document. And in the answer that the server sends, we have some encrypted values or encrypted document identifiers. Now, in some schemes, they could be unencrypted, but those schemes are called response revealing schemes. But we are mostly focused on response hiding schemes, so our responses will stay encrypted. And for as far as update tokens are concerned, you can see that there are sort of a tuple of pairs of encrypted versions of keywords and document identifiers. All right, so now we know what structured encryption is, but in order to essentially prove that the structured encryption scheme is secure against an adversary, we use the following security notion. This notion guarantees that the setup algorithm and the encrypted structure reveals no information about the underlying structure beyond the setup leakage LS. The query algorithm reveals no information about the structure and the queries beyond LQ. The update algorithm reveals no information about the structure and the updates beyond LU. If this holds for adaptively chosen operations, then the scheme is said to be adaptively secure. So in most schemes in literature, we have a simulator-based definition to capture this notion of security, but we'll skip that in order to conserve time, so that as it's not really like needed for this talk today, I think. So I think that's all on background, and we can move on to the main meat of the paper. Sorry. So we've already talked about the need for and the basics of structured encryption and adaptive security against a persistent adversary. Next up, I'll talk about what is dynamic volume hiding and why do we need it. Dynamic here essentially means that the schemes support an update operation along with a query operation. After that, I will present one of our fully dynamic volume hiding schemes on which all of our other constructions on the paper are based on. I'll briefly talk about our other constructions and what they bring to the table, but I think I'll mainly focus on 2CH. We'll see some nice graphs at the end, and then I'll conclude this talk by rehashing our key results. All right, so if anybody has any questions during any time, they can stop me, by the way. Okay, so volume hiding, as the name sort of implies, the goal is to hide volume. But essentially, when we say volume, we're talking about the volume of keywords in an encrypted multi-map. So let's look at this multi-map, for instance. Keywords are mapped onto tuples of values that are of different sizes. So W1 is mapped to a tuple of size 3, W2 to a size 1, and W3 to a size 2. goal of volume hiding is that these lengths are not revealed to this adversary during setup, query, update, like all the protocols, like never. Um, but why do we need to hide this volume? We need to hide this volume. Like one, it's always good to suppress leakage whenever you can. But other than that, you have quite a few attacks over the recent years that exploit volume leakage. And I've not mentioned all of them here, just a couple, but the volume attack in 2019 by Blackstone et al. Was very bad, which even worked on ORAMs, and it conveyed the urgent need to have dynamic volume hiding structure encryption. Uh, but attacks are one thing. But in order to develop some intuition that why the volume leakage is bad, we take an example of a hospital setting. Doctors, they might decide to store medical information of currently hospitalized patients in an encrypted database. When a patient name is queried in that database, the size of the result could potentially reveal information like how many tests the patient has undergone. This information could help an attacker in learning more about the patient, even their names, if they have some auxiliary information as well, even though everything was encrypted during the whole process. Just by the volume, they're able to, exploit. They're able to exploit the volume to learn a lot more, the attackers. Okay, so what it boils down to is that we want to hide query response lengths. And response lengths can leak during queries, and they can also leak at setup or updates for various schemes. So basically, we need to hide response lengths across the board, across all our protocols. And prior work has mostly dealt with static volume hiding schemes, which are encrypted multimaps that do not support updates. In case of KM19, the paper by Seni and Tariq on static volume hiding, we have semi-dynamic schemes, which mean that they do not support all different types of update operations. In our work, we wanted to keep query and update overhead as close to static schemes as possible in order to keep them efficient. And we also want basically achieve the first fully dynamic schemes that are volume hiding. So before we go into our scheme 2CH, I'll just quickly talk about what volume hiding leakage functions are. So similar to volume hiding game in a static setting that was in the paper by Pargiano et al. In 2019, we have a game-based definition to prove that a leakage function of a dynamic structure encryption scheme is also volume hiding. So in this game, we have a challenger on the left and an adversary on the right. The adversary picks two multimaps, MM0 and MM1, and sends it to the challenger. The maximum size of each of these multimaps cannot be larger than n, and the maximum volume of any label in both of these multimaps cannot be larger than m. Now, the challenger C picks a bit B and sends the setup leakage of MMB to the adversary. So essentially tosses a coin and then picks one of the multimaps and sends the leakage to the adversary. Now, the adversary can now send queries to the challenger, and the challenger basically gets to send back the query leakage on MMB. The challenger also applies the query to the other multimap, which let's call that MMB hash, because we want to make sure that we want to make the game non-trivial for the adversary to win. So the challenger always applies the query to the other multimap just to check that the maximum size and maximum volume restriction is not violated by the query that the adversary is sending before it sends back the query leakage to the adversary, basically. So anyway, so the adversary can now send two different updates to the challenger. These two, the update UOI applies to MM0, and update U1I will apply to multimap MM1. The challenger will only send back the leakage on, again, MMB and update UBI. Now, again, the challenger applies these updates, each of these updates to their respective multimaps, just to see if the maximum size and maximum volume restrictions are not violated. If they're violated, it will abort the game. And if they are not violated, then it will send back the leakage. Now, the adversary will keep sending query and update operations for as long as it wants. And then at the end, it will try to guess what the bit B was.
Ghous, sorry,
Yeah.
I have a question, actually, two questions. So
Yeah.
are we saying that both the multimaps contain the same set of labels? Is that an assumption here?
They don't have to, but the adversary, when the adversary queries, I was getting to that actually, that when the adversary queries, it obviously sends like it's essentially sending the same query to both multimaps, right? And when it sends an update, we have to make sure that in order to make the game non-trivial, the pair of updates that the adversary sends are on the same label and have the same type. The only thing that can vary are the sizes of the update, the tuple sizes of values that are sent, during an update.
Like, I'm assuming that, in first step, when the adversary sends MM0 and MM1, if they contain different labels, then it becomes trivial for adversary to win the game by querying, right? Because when the adversary sends WI, which is just present in one multimap but not the other. So
So I think a better way to phrase what I said is that we have the query leakage of WI should be same on both multimaps, which essentially translates to that the adversary cannot send queries for for label that exists in one and doesn't exist in any other.
Okay.
Yeah.
Okay.
The query leakage needs to be same on both multimaps. Yeah.
Okay.
And that is why even in updates we are restricting that updates on both label. Both updates that the adversary is sending for the different multimaps, it needs to be on the same labels and it needs to have the same type of operation. Only the tuple lengths can vary, and that's intuitively where the volume hiding part comes in. If the adversary wins the game, then it basically is able to differentiate between different volumes, essentially.
Okay, thank you.
Okay, so by using this scheme in our paper, we essentially prove that our leakage functions, we prove our leakage functions to be essentially volume hiding. Yeah. Anyway, so moving on to the construction, the first construction, 2CH. Where our goal, yeah, go ahead.
Sorry. Yeah, this is Sunny. So if you go back to the definition, this is slightly stronger, right? Because it's also guaranteeing, it's also hiding something about the entire multimap itself. So it's not just hiding. So it's saying that the leakage is not only hiding the response length, it's somehow also hiding the something about the multimaps, right? Unless you're assuming that these multimaps have exactly the same size and the same, the same parameters. Because an alternative definition could have been something like there's one multimap, but then there's two different queries, right? For possibly two different labels with two different tuple sizes.
If I'm understanding you correctly, and I feel like what I'm thinking right now is that the two multimaps, we essentially want to hide the volumes of different labels within those two multimaps as well, right? We just don't want to hide volume when queried or when updated.
Right.
Even in set a protocol, we want to hide that volume. So I think
exactly.
That might be the reason that it feels stronger.
Right.
But yeah, I can think on spot. But other than that, I'm happy to think about this offline. But I'm not super sure.
Yeah, that makes sense. Yep.
Yeah. Okay. Okay, so for 2CH, our first construction essentially, our goal is to keep the dynamic encrypted, keep the dynamic encrypted multimap to be volume hiding and to have an optimal overhead on both queries and updates at the same time. And we don't want to use any expensive cryptographic primitives. We just want to use like standard search, like just encryption and PRFs, which are being used in like previous works, previous state-of-the-art works. All right, so for 2CH, let's say we have an input multimap on the left side of the screen, and we have this visualization of what our encrypted structure would look like once we populate it over the course of the next few slides. So for a protocol to work, we needed a hashing scheme, and it will become clear as to why when I go over the set of protocols. So bear with me on this. In the static volume hiding construction by Patel et al. In 2019, they used something called cuckoo hashing, which you don't need to worry about if you don't know what that is. But essentially, what you need to know is that for in a dynamic setting, the cuckoo hashing algorithm did not seem suitable for volume hiding during updates. Next, we thought about using balls and bins hashing scheme to do updates and retrieve values from our encrypted multimaps, but we wanted to be more efficient than what balls and bins was giving us. So we finally found the right hashing scheme, which was the hashing scheme, the two-choice hashing by Azar et al. And we used that as a building block for our scheme. So how it works is as follows. Think of the gray lines on the screen right now as like different bins. I guess horizontal bins, which will contain encrypted pairs of keyword and identifiers by the end of this protocol. So we parameterize our scheme with the maximum size of the input multimap n and the maximum possible size of a label volume m. And we bound our bin sizes to be log n. And which basically translates to that we have a total of n bins, and each bin size is like log n. So and as similar to in the hashing scheme of Azar et al., we also have a client stash, which will store if any of the bin overflows, which will store values if any of the bin overflows. So now we basically, the first step is to hash all these keyword identifier pairs into the bins. So in two-choice hashing, each pair, so pair, when I say pair, I mean right now the arrows are pointing to ID4. So what I mean is the pair W1 and ID4. In order to put this inside the bin, the two-choice hashing would give us two bins, and we will put this pair in the less loaded bin. Right now, both are unloaded. So both are like zero load, so we can just put it anywhere. So we'll put it in the first bin, W1 ID4. Now, and it will be encrypted, of course. Now, we'll pick up another pair, and in order to put that, we have these two options, and by the hashing algorithm, and then we put W2 ID3 in one of the bins and then encrypt it. And in the same way, we basically fill all our data structure. Now, we need to pad this data structure with dummy encryptions. This padding will help us hide the volume during query and update operations. And sorry. And this concludes the setup protocol. So now, once we have this structure, the query works as follows. So during the setup, each value for a keyword had an option to be placed in one of two bins. So we have during query, we have to retrieve both of those bins by sending the bin numbers to the adversary essentially. So let's say for a keyword W1, I generate this token and I send this to the adversary, this locked W1 thing that you see on the screen. The query token is essentially like rederive the same choice of bins for each value of W1, just the same choices of bins that were derived at setup, essentially. So you don't need to worry about what all of this this terminology on the slides. All you have, the key takeaway here is that this is some sort of keyed hash function which takes in the key k, takes in the keyword which is to be queried, and then you have an appended one in the middle, which basically stands for value 1, and then you have an appended 1 and 2, which stands for if you can, I don't know if you guys can see the pointer on the screen, but I'm essentially pointing to 1 and 2 at the end of both of these H lines. And this basically stands for the bin choice, bin 1 or bin 2 for value 1 of W1. So in the same way, for value 2, we generate 2 bin options, value 3, we generate 2 bin options, and up to value M, we generate 2 bin options for W1, that where M basically, if you recall, is the maximum volume a label could have. We send this to the adversary, and the adversary returns us 2 M bins. Basically, we sent 2 M bin numbers, and the adversary essentially sends us 2 M bins of log n size. So locally, then the client will decrypt these bins and find the result for W1 and be done with that. Even though we're not going into much detail about the tokens, it is good to know that there's a standard way which we can use to send smaller token sizes to the adversary. So in the last slide, you saw that the client was sending 2 M tokens to the adversary, but there is a way that you can essentially send one evaluation of a hash function, and the adversary can compute all the 2 M bin numbers on their own end. So it's just good to know that we don't have to send so many tokens to the adversary. So moving on to the update. Update for a keyword can take the following forms. So update could be a new value that is being appended to a tuple. You may be deleting a value from a tuple. You may be editing editing a tuple. Sorry. You could be removing the key value tuple altogether. So an update for this protocol works in the following way. Basically, client will execute the query operation on the keyword that you want to update. So when you execute the query operation, the server will send the 2 M bins back to the client, and the client basically will perform the update on these downloaded bins locally, and then it will re-encrypt and upload those 2 M bins to the server. And in that way, the client is able to essentially do its update operation, and the server doesn't sort of learn any volume of your tuples for the particular updated keyword. Now, the setup leakage is essentially the upper bounds NNM for our construction 2CH. The query and update leakage are essentially, for both the query and update leakage, the leakage essentially is is key equality. And let me quickly explain what key equality means here. So imagine a series of operations that include query and updates on various keywords. Some keywords might be repeated, some might not be, but that's fine. It's just a series of operations series of operations containing queries and updates on various keywords. So key quality leakage essentially leaks to the server which of these operations were on the same keyword. So it sort of gives some sort of history to the server that, okay, this keyword was searched before, this keyword is updated before, and so on, obviously without knowing the keyword in plain text. But the cost of mitigating this leakage turns out to be logarithmic and identical to using oblivious rams, as shown in the paper by Pargiano et al. In 2019. The other leakage that the 2CH incurs is the type of operation, which is whether I'm doing an update operation or I'm a query operation, because they have very different signatures essentially. But this can be mitigated. So the only difference in the signature is that the updates essentially, in the update you essentially query first, but then re-upload. If in queries you start doing the same thing, basically re-encrypting and re-uploading after a query is done, then essentially from a server's point of view, there won't be any difference between the two operations. And this is a dynamic volume hiding leakage function according to the definition, game-based definition we discussed earlier. So as far as the efficiency of the scheme is concerned, the update and query complexity are basically m log log n, where log n is essentially something we can ignore, and m is just the maximum volume of a label. The EMM size is n log log n, but the good news is that we have a big O of n variant at no additional cost. So there's no blow up in size, which is great. It uses it basically stores the multimap in some sort of binary tree structure, which I won't go into. But good news is that we're able to save space by sharing some physical memory between various values. And now the stash size is for basically is the same as it for the underlying hashing scheme, which is omega of log n. And we have like tight proofs for that, but practically speaking, when I implemented this scheme, I never saw the stash size going more than log n. Especially never saw, actually it was always way under log n. So so that was good. Now I'll briefly talk about
Ghous,
yeah, sorry.
So just have a question about like just to make sure that I understand like one thing, which is what you mean by capital N. Like here,
okay.
So here, like usually, like in static cases, n is just the number of pairs, like in the multimap. Like
yeah, I mean the same.
Yes, okay. But then I'm a little bit confused to the following. So basically, this is a dynamic setting in the sense that tuples will increase in size, and you are assuming that m, capital M, is the maximum value that any tuple can have in the future, in the sense of size.
Yeah.
Right.
Yeah.
And this is kind of like the way how I view m and n is that those are two independent and different. At least like it's not clear to me. Like, I mean, in the asymptotics, maybe like this is what's happening. There is a relationship that you are assuming underneath between m and n. But let's say that you start with a multimap that has a very, very small n, like number of pairs. And then you are saying that the number of bins is n, and the number and the load of the bins is log n.
Yeah,
but
so
then,
sorry. Just to correct you quickly so that so n here is the maximum size of the structure, and like m is the maximum volume that it can have in the future, and is also like the maximum size. So sorry, just like
okay, so
because this scheme 2ch, essentially the first scheme, and it doesn't really care. It's like taking this for granted that m is the maximum volume and is the maximum size. The other schemes we have like sort of try to, remove this restriction of like n being like known from the start. But anyway, go ahead. Sorry.
No, that makes complete sense. So now n is not like really the same meaning that we usually have in static construction. Is n is actually n max, which is the maximum number of pairs that you ever have. Okay,
right.
Okay, thank you. Yeah.
Okay. All right. So I'll briefly talk about the other main constructions and why we needed them. Like, so the problem with this scheme that we had, among obviously there was the problem of like having m and n to be known in advance, but the other problem was that it wasn't for private, which all structured encryption dynamic schemes that are considered state of the art are. I didn't go into for privacy before, but I think all you need to know for the purpose of this talk is that for privacy kind of postpones the update leakage to query time, and which our 2ch scheme clearly doesn't, because at update time it leaks key quality as well. So in order to not have that issue, we have had another scheme, which was 2CHFP. F is for forward privacy, B is for back privacy, another term that I didn't describe, but again, I don't think that's, you should worry about that, but it's good to know that the scheme has multiple security properties. It is done, this is achieved by having a separate encrypted multimap to store updates until the updates are applied back to the original structure that was in 2CH at query time. This is a very standard technique used in previous schemes in order to achieve our privacy. But it also gives the standard problem of having the client state to be in the number of labels, because we need to sort of keep a counter for our privacy purposes and so on. So the state, we incurred this as a state cost here. Then we came up with another scheme, which kind of like the S here represents a small client state. So we basically tried to remove this the client state, the for private client state, by having static 2CH schemes in a hierarchical fashion on the server. We can talk about this offline, but it's all in the paper. We were able to remove this client state, and I think some earlier works also sort of used similar techniques, but not for the same purposes, I think. But anyway, so the problem still remains is the fixed upper bounds on the size of multimap and maximum volume of label. And so we finally have a section in the paper that talks about the rebuild functionality for both of our prior schemes. And but the rebuild functionality will essentially be able to do is remove that issue of knowing all of these sizes in advance. It kind of takes inspiration from how vectors are implemented in C++, where you give something double the space it needs and then double it and then keep doubling it and so on. So in terms of implementation, we have all the schemes implemented in Rust, which are about 600 lines of code each. We used for encryption, we used AES in CTR mode, and for PRFs, which we sort of used to basically hash the buckets, hash values to bins. We implemented that using HMAC with SHA-256. Experiments were done in memory, and we did these experiments on a PC with 64 GB of RAM. So for setup times, if you see 2CHFP and 2CHSFP, both of them have very similar setup times, mostly owing to the fact that most of them, their setup protocols are very similar to 2CH itself. In fact, I think 2CHFP has the same setup protocol as 2CH. But anyway, so on the x-axis, we have the total number of label value pairs inside the encrypted multimap. And on the left-hand side, you have time in seconds. Sorry, I think it got cut when I put it here, but this is time in seconds. And we see that it's around 36 seconds, 37 seconds. We can set up the encrypted multimap with 2 raised to 22 pairs, which is I think it translates to 4 million pairs. And this is what a lot of papers these numbers make a lot of sense in the industry, and a lot of papers previously have used these exact same numbers for their results, like the number of value pairs, I mean. So 36 seconds to set up a EMM with almost 4 million pairs. Okay, so for query, yeah.
Sorry, because I have a question. So here in the setup time, so when you fix, so let's for example, let's say that you have a multimap that has 2 to the power 20 label value pair. So do you need also to fix the n max? Because there is a difference between n and n max, because n max is the maximum number of pairs, which is where you have all of the number of bins that you have set up.
Right.
So have you picked different nmax for different pairs, or have you just said, okay, let's pick an nmax and vary the graph for that fixed nmax?
Yeah, this number of for setup for the setup experiment, we basically this 2 to 22 here is both n and nmax because setup is sort of static, right? So it's sort of the worst case where you have 2 to the 22 pairs exactly, and that's also the nmax. So basically fill everything up, right?
Mm.
So that could there doesn't seem to be a more worst case for that, if that makes sense.
I mean, I see what you are saying, but I think that it's also interesting to see the other case, which is basically like, let's say that you have, let's say you start with a small multi-map, right? You start with a small multi-map that has like, let's say just a thousand of pairs. And the goal is that you want to use this multi-map in the future for the next upcoming years, let's say 2 or 3 years.
Right.
So you need to also choose at setup like some nmax, which is maybe like 2 to the power 30 or 2 to the power 40, depending on how many pairs you will store in the future.
Okay. Yeah, so then, that's a very good point. Yeah, go ahead.
Yeah, exactly. Then you will have like also like some difference in terms of evaluation, because like depending on the gap between n and the nmax, you will have different setup times.
Yeah, I agree. Yeah. Okay, so here this is the graph for query times. On the y-axis you have time in milliseconds, and on the x-axis you have the maximum volume for a label, that basically m that we talked about in previous slides. The different lines in different colors are basically different nmaxes. Sorry, are different nmaxes, and essentially what's happening is that how the experiment was run was that we queried like each point is computed multiple times for sure, but essentially how this experiment was run was that you had the keywords mapped to different lengths, but not necessarily the maximum lengths. But and we took like averages across keywords, and then it was averaged to per result. So this millisecond on the y-axis doesn't represent the time for the whole result of a query, but per result of that query, and which you can see doesn't go more than 0.05 milliseconds. And if you assume that the label has a maximum, like it was the results are like 16384, the maximum volume, it still won't go over a second. So, and it's very similar for both of these constructions. And finally, we have this update time graph. Here, it's not per result, and that's my bad. We should have made the graphs consistent in the paper, but this is the total update time. And again, the lines are n maxes, and the x-axis is like total maximum volume for a label. And as you can see, is that for two choice FP, we do not exceed 25 milliseconds for the maximum volume. But for two choice FP small, we exceed that 25 milliseconds. We actually have update times that are one level above the graph C, because they start from 48 milliseconds, and the previous graph, they go up to 25 milliseconds. The reason being that in order to get rid of the client state, a lot of things had to be kept on the server for 2CH SFP, and and so a lot more computation had to be performed on the server. But still, having an update time less than a second for big tuples is still a win. And now I think I'll conclude with the key takeaways, and we're almost out of time as well. So we made advances in dynamic volume hiding and designed the first fully dynamic volume hiding schemes with different security guarantees. The concrete efficiency for our 2CH is better than best known semi-dynamic schemes. I think we built 2 further practical schemes on top of 2CH to provide far privacy with all other existing guarantees such as backward privacy simultaneously. Something that wasn't done for dynamic volume hiding before. We gave a formal game-based definition of dynamic volume hiding. We implemented constructions in Rust and ran various experiments to determine practicality. We did a thorough evaluation of our schemes. The evaluation basically showed that our constructions improve on concrete performance of previous constructions. First, we observed that our fully dynamic constructions have queries a cost that's comparable to previous static constructions, which is great. That means that we are adding dynamicity with little to no extra cost on the queries. The schemes also improve query communication cost by 2 to 3x over the best known semi-dynamic volume hiding schemes, while providing stronger privacy guarantees. And yeah, with that I wrap up. Thank you. And yeah, questions, anything?
Yeah,
I have, oh,
thank you. Thanks, Ghous, for the talk. And it seems that we have already some questions. Yeah, go ahead.
Okay.
I just have a small question. So generally for these schemes, when we prove their security, which is essentially that the scheme doesn't leak anything beyond what is given by leakage
Yep.
functions, we have this simulator-based definitions. So is it the case that for these constructions, you prove 2 definitions, one to show that do not leak, the schemes
Yeah.
do not leak beyond. Okay.
So this the simulator-based definition, the standard definition for security stays, and the scheme is proved to be secure under that definition. The other game-based definition that I talked about was on the leakage function itself.
Right.
So
Okay.
we are basically proving that the schemes are secure under standard, simulator-based definition, and then our functions, our leakage functions are volume hiding leakage functions.
Okay. Thank you.
So I have a question as well, and this one is more from a parameters perspective. Like, I was thinking a lot about it when you were giving the talk, which is like how n max and m max relate. And I think that this is really a valid question in the sense that you may also say, okay, how my tuples vary in the future? Like how my tuples length vary in the future? So have you given some thought like about how to relate these 2 parameters? Is it like something like, for example, if I want to implement your scheme, should I go to pick n max equal to m, the capital M times the number of labels that I have? Then this is like too big. How did you go to pick these 2 parameters in a joint fashion?
So to be fair, I don't think we have a dedicated section to parameter selection in the paper, and we didn't give it much thought at that time. But in terms of evaluation, how we picked these numbers were that we picked them independently. We didn't think of having a connect between them, but we took numbers from previous papers that came out of different companies that basically used actual industry use cases essentially to determine, how large the tuples get, or how especially the 2 to 22 number is something that seems to be very reasonable, at least for the cases that we were looking at over during my internship when we wrote the paper. So we just picked, I think, N and M depending on some data that we had at the time. We didn't, I think, scoped out how people would usually pick them.
Yeah, that sounds good. Yeah. Thank you.
Yeah, but I think, and also in some of the reviews of the paper as well, I think parameter choice is a very, I always feel it's like a paper in itself, but I think we could potentially work on this on the future. We should, but let's see.
Yeah, no, it's really interesting. For example, like there are already some constraints that these two parameters need to verify. Like m is strictly smaller than n, or equal. Like I mean, you can imagine it's smaller or equal. So there are already some constraints that we need to
Yeah,
have
yeah.
in order to pick these two parameters. Like, but yeah, I agree. Like that, it sounds like it's kind of it requires some also thoughts by itself.
Yeah, it's not something that you solve under 5 minutes.
No. Okay, so it seems like that we are already reached the time. It's noon. So thanks, Ghous, for your talk, and yeah, good luck for your next work. So hopefully we will see you again, like in the future, with some new results. Yeah.
Thank you.
Thank you. Bye.
Bye.
Bye, everyone.
Bye, everyone.